Hello everyone, welcome to the next lecture on the complex analysis. Today I will explain you how you can define the terms limit point of the zero. Myself Dr. Harish Garg, you can follow and subscribe my YouTube channel where you can find the playlist of the complex analysis. In this playlist you can see the last lecture was on the limit point of the zeros and other lectures related to the complex analysis such as singularity, maximum modulo principle, Taylor series, Lorentz series, and many more lectures available in this playlist. You can follow and subscribe my YouTube channel. Now, what we have discussed so far, we have defined the limit point of the zero concept, in which we learned how you can define the isolated essential singularities. Now, in this lecture, we will cover the concept of the limit point of the zero, and we will discuss whether the limit points of these poles are non-isolated essential singularities or not. Make sure the limit points of the zero are my isolated essential singularities, while the limit point of the zeros are the non-isolated singularities. But before that, all of us knows that if any point z0 or any function f has an isolated singularity at the point z0, then what does it mean? It means the function is analytic in the neighborhood of the z0. Or you can say once the function is analytic, we can expand the given series with the help of the Lorentz series. Now, the term which involvement of the negative power of the n, you can see this is the negative power of the n, and this component we call as the principal part of the Lorentz series, or we can say is the summation bn divided by z minus z0 raised to power n. As it involves the negative power, so we call as the principal part of the f. Now, since our target is to define the limit point of the pole, so firstly I will tell you what is a pole. The basic definition of pole is if you consider the principal part of the Lorentz series and clearly say if I open them, it will be b1 over z minus z0 plus b2 divided by z minus z0 square plus and so on. If I consider this is the m divided by z minus z0 raised to power m plus and so on. Now, what does the meaning of the pole? We will look about all those coefficients of the bi's which are my non-zero. For example, if I say bi are my non-zero up to the value of the m and b of I plus 1 is my 0 whenever I is greater than of the m. That means up to this term all are my non-zeros, while after that the terms are my 0. Then we can say the pole is of order m. Or you can see if we consider the finite number of the coefficients bn, then we can say this bn or z0 is a finite pole of analytic functions. In other words, if I say bk is my non-zero for all and for bk is my non-zero and bn is my 0 for all n greater than k, then we can say that z0 is the pole of order k. For example, if you consider the function f of z, clearly say you can expand this series, expand the function with the help of the Lorentz series. Fine. For more details, you can watch about my this lecture of the Lorentz series, how you can expand the function with the help of Lorentz series. Once you can expand the Lorentz series, you will get this equation number 1. Now clearly say look at only the term which involvement of the negative power of the n. You can see there are the only two terms. It involvement of the positive power of the z. Now it involves only the two terms, and what is the highest degree? Highest degree is my 3. So therefore I can write this number is z is equal to 0 is the pole of order 3 because the highest power is my 3. Clearly say if you look about this quantity plus 1 over z. So clearly say b3 is a coefficient of the z 1 over z cube. b3 will be my 1. What is the b2? b2 means the coefficient of 1 over z square, but there is no coefficient. What is the b1? b1 is a coefficient of the 1 over z. And while all others b4, b5, b6 and all are my 0. Similarly, if you consider the next example, I can write this number is 1 over 1 plus z. Now clearly say there is only one term and the power is my 1. So therefore z is equal to 0 is the pole of order 1. or pole of order 1, we can also say z is equal to 0 is my simple pole. Fine. Whenever there is a pole of order 1, we call as the simple pole. And in this case, you can analyze that B1 is my 1, B2, B3, and all those others values are my 0. Now, based on these poles, you can see Z0 is my pole, Z0 is my pole. If you closely look about the functions, what is the value at the point Z is equal to 0? Can you say the function value? So clearly say it will goes to the infinity, or it's a 0 by 0 form. Fine. The first result says if f of z is a pole at the point z is equal to z0, then the function value will goes to the infinity as z approaches infinity. Now, proof is a very simple. I can give you the proof in the 2 or 3 lines. Assume the fz has a pole at the point, say z is equal to z0, which is of order m. What does the meaning of the m? That means bm is my non-zero, while bm plus 1, bm plus 2, all the values are my 0. Fine. So by using the Lorentz series, I can write as 1 to m of the b n or so. Fine. I can open this value. It is my b1 over z minus z0 plus b2 over z minus z0 square and so on. The last term is my bm over z minus z0 raised to power m plus summation n varies from 0 to infinity an z minus n. Fine. Again, I can see because it's a pole of order m, so I can take a common. I can take z minus z0 raised to power m is my common. Fine. So it will be my bm. What is the previous term is m minus 1 of z minus z0 plus and so on. This value will be my b2. If I take z minus z0 is common, so this number will be my m minus 2 plus what is the value of this b1 z minus z0 of m minus 1. Fine. Now you can simply take z approaches z0. The left hand side value is my and take the absolute value. So it is the absolute value. What will happen? This value will goes to the 0. This value will goes to the 0 because m is my greater than 1. This value will be bm. 1 over 0 is the infinity. This value will be the 0. So this number f of z will goes to the infinity as z approaches z0. Look at this counter examples. Find the pole of the functions. So remember how you can find the pole of the functions where f of z will goes to the infinity. So can I write this function is 1 over sine 1 over z? Fine. So how you can define the pole? The pole means where the function value will goes to the infinity. So when it will be the infinity? When sine of 1 over z will be 0. The pole of the fz is sine 1 over z is 0. Can you find the value of the z? 1 over z is my n pi, where n is my integers. So the value of the z is 1 over n pi, where n is my any integer. Look at the second case. How you can find the pole again? Where the function value will goes to the infinity. This value will goes to the infinity when z square plus 4 will be 0. So that means z square will be my minus 4 and that implies z is my plus minus 2 iota. Fine. Now since these are the distinct roots, so we can say these are my simple pole. Again, if I take n is equal to 1, 1 over pi, 1 over 2 pi, 1 over 3 pi, all are my distinct root. So again, these are called as my simple poles. Now, based on this example, you can see, or in other words, you can see 1 over zn is basically my sequence. I can consider this as a sequence where n is my integer. Find 1 over pi, 1 over 2 pi and so on. So the main result of this today is if the limit point of the sequence of the pole, the limit point of the sequence of the pole is always non-isolated essential singularity. Meaning is, can you find the limit point of this function? Limit point means whenever n approaches infinity of the z. What is the answer is 0. So this means the result say z is equal to 0 is my non-isolated essential singularity of the given function. That's the meaning of this result. The proof is very simple. If I consider z0 is the limit point of the sequence of the pole, so once this is my pole, what does the meaning? That means every neighborhood of the z0 contains infinite number of the points. So once you can say this is the pole, what does the meaning of the pole? That means f of z will goes to the infinity. That means the function is my unbounded. So that means you have the infinite number of the points where the function is unbounded. Once the function is unbounded, that means the singularity or the function is not analytic. Once the function is not analytic, what does the meaning of that? That means the point is not isolated. For more detail about the singularities, you must watch about my this lecture of the singularities in the complex variable or the complex analysis. So once you can see that Z0 is my non-isolated, hence Z0 is a non-isolated essential singularity. I will explain you the couple of examples. For example, if I consider f of z is my tan 1 over z, I can write this function is sine 1 over z divided by cos 1 over z. Is it fine? Now always remember, these are the numerator and denominator. Your first preference will always given to the pole. The pole means your first preference is always given to the denominator. If my denominator is a 1, for example, my function is z square plus 4 only. Fine. Now, since the denominator is 1, then you can give the preferences to the zeros. Then only you can find the zeros of the function fz, as I have defined in the previous lecture, limit point of the zeros. Now, can you find the pole of the functions? The pole of the function is when the denominator is 0. What does it mean? 1 over z is 2n plus 1 pi over 2, where n is my integers. Fine. Can you find the value of the z? Z will be my 2 over 2n plus 1 into pi. Now clearly say this is the sequence. For the different value of the n, you will get the different value of the z. So can you find the limit point of the pole? So therefore, the limit point of the pole is, can you find the limit point? That means you can take limit of the z as n approaches infinity. So what will happen as n approaches infinity is 0. So you can see the limit point of the pole is z is equal to 0. Therefore, by using the result, z0 is my non-isolated singularity of the given function. Look at the second example. I hope you can like and comment on the video as well. Examine the nature of the singularities at 0 and at infinity. First of all, clearly say z is equal to 0. Cot 0 is my goes to the infinity. Fine. So that means yes, this is the singularity. Always remember, if you calculate the value at the point z0, if this value will give you the finite, that it means it is no singularity. Fine. Now, so firstly, I can write the cot in terms of the cos and sine. This is my cos over sine. Fine. And then because the denominator is not a 1, so I can find the pole of the function. The pole of the function is when denominator is 0. This implies sine of pi z is 0 or z minus a square is equal to 0. That implies pi of z is my n pi, and that implies z is equal to a comma a. So this implies z is equal to n, where n is my integer, and in this case it is a comma a. Now because a comma a is a double pole and it's a plus minus n are my simple pole, because it will give you the 0 plus minus 1 plus all are my distinct roots or distinct value of the z. So yes, they are the simple pole. Now clearly say at this point, this is a sequence for the different value, so you can find the limit point of pole. So what is the limit point of the pole? Can you find the limit point of the pole? You can see z is my plus minus n. So if you take limit as n approaches infinity, this value will be infinity. Therefore, the limit point of the pole is infinity, and this infinity is known as non-isolated essential singularity. What about the z is equal to 0? So clearly say when you take z is equal to 0, this is my simple pole. So z is equal to 0 is my simple pole, while z is equal to infinity is my non-isolated essential singularity. Look at this one. Again, this is the cosecant. I can write in the terms of the 1 over sine, and at z is equal to 0, the function is infinite. That means, yes, there is a singularity. So we can find the pole by taking sine 1 over z is 0. That means 1 over z is my n pi, and this implies z is 1 over n pi, where n is my integers. And clearly say it's a sequence, so I can find the limit point. What is the limit point of the z as n approaches infinity? As n approaches infinity of the z, clearly say this is my 0. Therefore, the limit point of the pole is my 0, and 0 is the non-isolated singularity. Again, look at the tan. Again, I can write as a sine over cos, the singularity, or you can see the pole will be 1 cos 1 over z is 0. So I can write as value of the z is 2 over 2n plus 1 pi. Clearly say the limit point as n approaches infinity, this will goes to the 0. Therefore, 0 is my non-isolated singularity. Look at this next one. Examine the nature of the singularities of the chord z. I can write this is cos over sine z. Fine. Now, because the denominator is my non-zero, so you can find the pole of the given function is sine z is 0, and z is my n pi. Again, you can see this form the sequences, and once you can form the sequences, you can find the limit point. Can you find the limit point of the z? So the limit point of the pole is as n approaches infinity, it will give you infinity. Therefore, z is equal to infinity is my non-isolated essential singularity. Again, it's a cosecant. I can write as a 1 over cos z. I can find the pole is my cos 1 over z is 0. This implies 1 over z is 2n plus 1 of pi by 2, where n is my integer. Can you find the value of the z? This number is my 2 over 2n plus 1 into pi. So what is the limit point? Limit point is my 0, and the 0 is my non-isolated singularity. What kind of the singularity for these functions? I hope you can like and comment on this video as well. So can you find the pole of the given functions? The pole is 1 plus e raised to power z is my 0, or e raised to power z is minus 1. How you can find the value of the e raised to power minus 1? This is 2n plus 1 pi iota, because we all know e raised to power, I can write this in terms of e raised to power iota z is cos z plus iota sin z, and your target is to make this number to be the minus 1, this number to be 0, and we all know cos of n pi is my minus 1 whenever n is my odd, and it is my plus 1 when n is even. So once it is my odd, so you can write as a 2n plus 1 pi. So can you find the value of the z? Z is my 2n plus 1 of pi iota. Fine. Now again, for the different value of the n, it's a form a sequence. So you can find the limit point of the poles, which comes to be z is equal to infinity. Hence, infinity point is my non-isolated essential singularity. Now again, you can see at the point pi by 4, sine pi by 4 is 1 by root 2 minus 1 by root 2, that goes to the infinity. Yes, this will give you the singularity. Again, the denominator is 0, so I can start with the pole. The pole will give you the sine z minus cos z is 0. This implies tan of z is my 1. So can you find the value of the z? It is pi over 4 plus n pi, where n is my integer. Fine. Again, it forms sequences. Can you find the limit point of the pole? As n approaches infinity, so that will goes to the infinity. This means z is equal to infinity is my non-isolated essential singularity. But the question asking about only at the point z is equal to pi by 4. So there is no need to check about the limit point because they wants to be know the singularity at the point pi by 4 only. So how you can make them as a pi by 4? Clearly say when n is 0. When n is 0, your z is my pi by 4, which is nothing but my simple pole singularity of the given function. Okay, look at this another one. Again, it's a cosecant, so I can write as a, and your target is to check only at the point infinity. Now, can you find the pole? Again, because the denominator is a non-zero, so the pole of the given function is sin z is 0. That implies z is my n pi. Fine. So once the z is my n pi, can you find the limit point of the pole? The limit point of the pole is z is equal to infinity. So that implies, look at the next one. Again, your target is to identify the nature of the singularities of the given functions. Again, the denominator is a non-zero, so you can find the pole of the given function is z into 1 minus z square is 0. This implies either z is my 0 or 1 minus z square is 0. That give you z is equal to 0 and this value give you 1 and minus 1. And you can see all are my distinct, therefore these are my simple poles. Remember, you can never find the limit point of these poles. Why? Because this is not a sequence. Sequence is always considered when it involvement of the term n. But in this case, these are my simple poles. So discuss the nature. Natures are my simple pole. This is the way you can analyze the behaviors of the singularities. Again, I can recommend you can watch about my previous lecture of the singularities and the limit point of the pole for the more details concepts. We will see the next lecture very soon, and let's start with the next example. Discuss the singularity of the functions. Again, I can find the pole of the given functions. That is a z4 is equal to minus 1. How you can write the minus 1? It is e raised to power iota pi, or in terms of the n, as I mentioned you in the previous, it's an odd number 2n plus 1 pi iota. Can you find the value of the z? It is e raised to power 2n plus 1 pi iota divided by 4, where n is my integer. Fine. Now discuss the singularities. Now clearly say this is sequences. Can you find the limit point of the pole? Limit point of the pole as n approaches infinity, e raised to power infinity is infinity. Hence z is equal to infinity is my non-isolated essential singularities. On the other hand, if you look about for the different value of the n, if I substitute n is my 0, then this number is my pi iota by 4. If I substitute n is 1, then 3 pi iota by 4, n is equal to 2, 5 pi iota by 4, and so on. And all these are my simple pole of the given functions. Because they are not mention you about which point you are talking about the singularity. So I can find all those points, infinity as well as simple poles. Look at this next one. Again, because the denominator is given to be as a non-zero, so I can find the pole which give you the value of the z is my pi comma pi. So therefore z is equal to pi is my double pole. Fine, because it is does not involve any of the n, so limit point of the pole you can never calculate. So z is equal to pi is my double pole of the function. So I hope you can enjoy this session too, and we will see the next lecture on the argument principle very soon. Till then, you can share this video with your friends, like and comment on the video, and don't forget to subscribe my YouTube channel. Best of luck, students. Happy learning.